All right, so let's start. So today you are going to learn about magnetism. Okay. So I believe most of you have experience of working or playing with magnet. Okay. So you probably see a U-shaped magnet, something like this, or a button-shaped magnet, something like this, or a bar magnet, something like this. Okay, so many of the properties for a magnet is very similar to what we learn in electric charge. Okay, all right. So I will be going to learn one by one. Okay, so the first thing that I want to mention here for a magnet is it has two poles. Okay, one we call north pole and another we call south poles. Okay, similar to the electric charge, I mean like charge repel each other and opposite charge attract each other. Here we have the similar property. For example, here you see the north pole and north pole repel each other, south pole and south pole repel each other again, but north south are attractive. Okay, so that means like pole repel each other, opposite poles attract each other. Okay, so remember that it's very similar to positive and negative charge. Okay, all right. Now the next question is why we call a pole south pole or a pole as north pole. Okay, and it has some reason. Okay, the reason is if you if you uh, I mean tie a magnet, okay, with a string and let it freely move, okay, then you will see the one pole is toward the geographical north pole. Okay, so the pole is toward the geographical north pole, we call it north pole. So for example, you see this one is towards the geographical north pole. Okay, so you see this place is close to Canada, that means it is the geographical north pole. Okay, and the other side is if you are close to south pole, for example somewhere here, you will see that the south pole is towards this side. Okay, so yeah, the naming comes from these. Okay, and another thing I want to mention here is Earth actually behaves like a very big bar magnet. So here you see that we draw a bar magnet, okay, connecting the geographical north pole and geographical south pole. But the thing here is Earth's magnetic south pole is close to the geographical north pole. Okay, and opposite here, Earth's magnetic north pole is close to the geographical south pole. Okay, and because of this, okay, and because of this, north pole is attracted by the Earth south pole. I mean, any magnet's north pole is attracted by the earth magnet's south pole. Okay, and that's why the north pole is towards the geographical north pole. So yeah, you don't need to remember all those steps, okay, all those things. You just need to know that uh, earth is a very big magnet. Okay, and earth's south pole, magnet's south pole is close to the geographical north pole, and magnetic north pole, I mean earth's magnet's north pole is close to the geographical south pole. Okay, all right. All right, so earlier in chapter 16 you see that we can have single positive charge or a single negative charge, but it is different here. We cannot have single south pole or single north pole. Okay, so when you break a magnet, okay, when you break a magnet, you get two separate magnets. Okay, so for example, if you break here, you get two other magnets with their separate south pole, north pole, south pole, north pole, and so on. Okay, so remember that monopole, magnetic monopole is not possible. Okay, all right. All right. Now you already know that magnet attract some materials. Okay, and not all materials are attracted by the magnet. Okay, and based on that we categorize materials in three category. The first one is ferromagnetic material. Okay, so what is the ferromagnetic material? Ferromagnetic material means these materials are strongly attracted by the magnetic field. Okay, and what are these materials? These are iron, cobalt, nickel, gadolinium, and some of their oxides and alloys. Okay, the second category is paramagnetic materials. Okay, and these materials are weakly attracted by the magnetic field. And what are these? The two examples are magnesium and lithium. Okay, and third category is diamagnetic materials, and these materials are weakly repelled by the magnet or magnetic field. And some examples are copper, silver, gold, etc. Okay, all right. The next thing is the magnetic field. Okay, similar to the electric field represented by using the electric field line, we use the magnetic field line to represent the magnetic field. Okay, and it's very similar to electric dipole. So remember that if we have a positive charge and if we have a negative charge, the electric field line was something like this, right? Something like this. Okay, so if you replace the positive charge with a north pole and a negative charge with a south pole, um, uh, what you get is basically that the magnetic field. Okay, so you see that um, uh, the magnetic field line starts from north and at south. Okay, and so on. Okay, so if you replace positive charge with north pole and negative charge with the south pole in a electric dipole, what you get is basically the magnetic field. Okay, uh, so this is the magnetic field lines uh, for a bar magnet. Okay, so the line starts from the north pole and ends at south pole. Okay, similar to the electric field lines start from the positive charge and ends at negative charge. Okay, and the other properties are very similar to the electric field lines. Okay, so for example, okay, so this I already mentioned that magnetic field lines exit from the north pole, that means start from the north pole and enter the south pole. Okay, and at the south pole the direction of the magnetic field is tangent to the field line at any point. Okay, so it was very similar in electric field line also, right? By the way, we don't use M in this textbook to represent the magnetic field. Okay, we use B for some reason. Okay, so in some textbook they use M, but because your textbook use B, I am going to use also B for magnetic field. Okay, all right. The next property is the number of lines per unit area is proportional to the strength of the magnetic field. Okay, you also see this in electric field. The number of lines per unit area is proportional to the strength of the magnetic field. Okay, and uh, parallel lines, something like this, means the uniform magnetic field. Okay, and you can get uniform magnetic field between two wide poles of between two wide poles of magnet. Okay, so here you see that it is a very wide north pole and it is a very wide south pole. So between two wide north pole and south pole, you can get a uniform magnetic field. That means parallel magnetic field lines. Okay, all right. So far, what we learned is that we can have magnetic field from a physical magnet. Okay, but beside this, we can have also magnetic field from a current carrying wire. Okay, so first let's look at this simulation. Okay, all right. So here you see that we have a circuit and circuit is not closed. I mean, switch is not closed. That means there is no current flowing through this circuit. Okay. And on the right hand side, there is south, north, east, and west, means these are the the direction, I mean the geographical direction. North means to the right, south means here to the left, west means at top, and east means bottom. Okay, so it's kind of here it is the direction of geographical north, south, and west, east. Okay, so you see that a compass here on the, so this is the compass. Okay, so the compass here is basically on top of the circuit, and now as usual the direction, the red here is the north pole and blue means the south pole. Okay, so you see the north pole is to the geographical north pole and south pole is towards the geographical south pole. Okay, so that means it is um, it is not deflected, it is basically freely moving, uh, freely moving compass, and it is now just influenced by the earth's magnetic field. Okay, and that's why it is towards north and south of the earth's I mean earth's I mean earth. Okay, now if we close the switch, okay, you will see that there is some deflection. Okay, so deflection means there is another magnetic field which basically deflect the magnet and the compass's magnet. Okay, let's see. Okay, so you see that, so when there is a current, okay, when you close the switch, that means there is a current in this circuit, and because of the current there is a magnetic field, and this magnetic field deflects the compass's needle and the compass's magnet. Okay, so this proves that there is magnetic field when current flows through the wire. Okay, now here few things we want to understand. Okay, so if I increase the current, you will see that there will more deflection. Okay, oh okay, so not this one, so here. Okay, okay, so there is a current, there is a magnetic field. Okay, so this green arrow in the right hand side, it's basically showing the magnetic field. Okay, so if I increase the current, okay, so you see that it increases the magnetic field. Okay, so I'm increasing the current. Okay, so that means the current and magnetic fields are proportional to each other. Higher the current, higher the magnetic field. Okay, now if I switch the direction of the current, you will see the direction of the magnetic field is also um, switched. Okay, now you see that it is going from right to left, I mean in one direction, and if I switch the current, you will see that it will be in opposite direction. The I mean the magnetic field direction is opposite. So have a look. So you see now I change the direction of the current and it changes the direction of the magnetic field. Okay, so two things here you learn. One is higher the current, higher the magnetic field. Second is when you change the direction of the direction of the magnetic field is also changed. Okay, now before I move on, let me tell you how we can determine the direction of the magnetic field by knowing the direction of the current. Okay, so we can do that by using something called right hand rule. Okay, so look at this picture. Okay, so if you use your hand something like this, then the thumb is basically tells you about the direction of the current, and this finger, basically other fingers, is basically telling you the direction of the magnetic field. Okay, so if I go here, you can see also this. Okay, so you see that the current direction is upward, that is shown by the thumb, and then you see the other finger's direction is showing the arrow's direction. Okay, if we switch the current, you will see the opposite. So you see that. Okay, so remember that this is called the first right hand rule. So you are going to learn two more right hand rule. Okay, all right. Now that is a very simple one. when the current is a straight line, I mean the wire is a straight line, but we can have also something like this, okay, a loop where the current is flowing in this direction. But no matter whether it is a straight line or a loop, okay, you can use the first right hand rule to determine the magnetic field's direction. Okay, so for example, here you see that this is the direction of the current and this is the direction of the magnetic field. So here in the second picture you see the magnetic field's direction, okay, for a loop. Okay, so when we have more loop, you see that it's basically very similar, but um, the magnetic field is stronger here inside. Okay, that I'm going to show here in this simulation. Okay, so let me start with one loop. Okay, all right. Okay, so you see that we have battery. Okay, battery has 10 volt here, so that means there is a current in this circuit. Okay, so here you see a loop. Okay, so in this circuit we have current, and because of this current you see the magnetic field direction showing by these small magnets. Okay, now let me use a magnetic field meter. Okay, so this meter basically tells you about the magnetic field, the magnitude of the magnetic field at any at any point. For example, here it is showing the 0.76 unit. Okay, I'm going to talk about the unit later, but focus just on the magnitude. Okay, so here for example it's showing the 2.94. Okay, so at this point when we have one loop the magnetic field is 2.94. How about when we have two loops? So you see that two loops, when we use two loops the magnetic field increases. Okay, how about three loop? So you see that it is more, and it is even more. Okay, so um, this simulation tells us that when we have more loop, okay, the current is more, and that means the magnetic the when we have more loop the magnetic field is higher. Okay, I mean here the same current is flowing. I mean it's not the I mean getting more loop, it doesn't mean that there is more current. Okay, so more loop means more magnetic field. Okay, so remember that. Okay, and that's why we have more magnetic field here. And another thing you can see here uh, is the lines are parallel inside the loop. Okay, so because lines are parallel inside the loop, okay, it means that there is uniform magnetic field inside. Okay, all right. All right, the next thing I'm going to talk is the force on magnetic force, basically on an electric current in a magnetic field. Okay, so here look at this two picture. Okay, so here in both picture we have a magnet. Okay, so you see that we have magnet and a current carrying wire. I mean a wire connected with a battery. That means this wire is basically carrying a current. Okay, so we already know that we have a magnetic field here from the magnet, and when a current is going through this circuit, okay, in this wire there will be another magnetic field. So we have two magnetic field here, one from this magnet, physical magnet, and one from this. Okay, now you know that here we have two magnet or two magnetic field, and they will be either attracting each other or repulsing each other depending on the polarity, right? Now this I'm going to tell you here. Okay, so before I talk about the mathematics, okay, let me show you these. Okay, so here you see that the circuit is in the left hand side, and what is going on is showing in the right hand side. Okay, so here first let's talk about the circuit. So you see that we have a power supply, and power supply is connected to two conducting rod. So this is a rod, this is another rod, and this rod, and there is another movable rod, this one. Okay, and this movable rod is inside a magnet, inside a U-shaped physical magnet. Okay, so that means there is a magnetic field. Okay, so in the right hand side you see the magnetic field directions. Okay, and then um, what you see, that if I try to bring this here, it is repelling. So this rod is basically repelling by this magnetic field. Okay, so you see that. If I switch the direction, so here I can switch it, so you see that then it is attracting. Okay, so if I bring it here, you see that it attracts. Okay, so that's because we have now two magnetic field, one from the um, physical magnet and uh, one from the circuit. Okay, all right, now let me go back here. Okay, first let me talk about the math. Okay, and then I'm going to talk about the direction. Okay, so what is the magnitude of the magnetic field or magnetic force here? Okay, so it is this: F is equal to I L B sine theta. Okay, to understand this expression, let's consider um, this diagram. Okay, so here you see that we have a uniform magnetic field B. Okay, and the direction is from left to right. And let's say we have a current carrying wire, this one, and this part, okay, whose length is L, is inside the magnetic field only. Okay, so if we have some situation something like this, then the force is, the magnetic force is I, where I is the current. Okay, L is the length of the current carrying wire that is inside the magnetic field, and B is the magnetic field, and sine theta is the angle between the magnetic field and the wire. So here you see this is the theta. Okay, now you see that the maximum value of sine theta is sine 90 degree, right, and which is equal to 1. So the maximum value can have I L B, okay, when theta is 90 degree. Okay, so that means when the current carrying wire is perpendicular, okay, then this angle is 90 degree. Okay, so that time we get maximum force. Okay, on the other hand, sine 0 degree or sine 180 degree is 0. Okay, so that means the force is equal to 0. So the minimum force we get when the current carrying wire is parallel to the magnetic field. So if the current is in this direction, okay, if the current is flowing in this direction or in this direction, okay, then we get zero force. Okay, so remember that. All right, now let me talk about the direction of the force. Okay, how to determine the direction of the force. Okay, so here in this simulation you see that one time it is in this direction, and in another time is in this direction. Okay, so we need to understand for an arbitrary situation, when we have an arbitrary diagram. Okay, if we are given the arbitrary direction for the current and the magnetic field, then how to determine the direction of the force, direction of the magnetic force. Okay, so we can do that by using the second right hand rule. Okay, so what is the second right hand rule? Second right hand rule is this one. Okay, so your index finger if your index finger is telling about the current, other three finger is telling about the magnetic field, then the force will be the thumb. Okay, so you have to do little practice. Okay, so try this one for one of these, either for this and this, and you can see that for this one, for the first one, the force will be downward, and for this one the force will be upward because the current direction is different here. Okay, so the current is the index finger, other three finger is the magnetic field, and then thumb is the force. Okay, and it is only, I mean, you can use only right hand to show that. Okay, to determine the direction of the force, you have to use the right hand. So that's why it's called the second right hand rule. Okay, so by using the second right hand rule, you can show that the direction of force here. Okay, so you can show that the direction of the force here is into the screen. Okay, so use your right hand. Okay, so the index finger should be here in this direction. So this is the index, and the other three fingers are these. Okay, other three fingers, and then you can show that the thumb is into the screen. Okay, so now you see it's very difficult to show when the direction is into the screen or the out of the screen. Okay, to do that, to represent the into the direction into the screen or out of the screen, we use some notation. Okay, so this is the notation. Okay, so if any direction is into the screen, then we use cross sign, and if any direction is out of the screen or out of the page from your textbook, is this direction. So use this symbol to do that. Okay, dot means out of the screen or out of the page, cross means into the page or into the screen. Okay, so remember that. Now similar to the electric field, magnetic field is also a vector quantity, and the SI unit is Tesla, and we use capital T to represent Tesla. Okay, now from this equation, okay, what I derive here, okay, you can show that B is equal to F max over IL. Okay, and this equation tells you that 1 Tesla is equal to Newton over ampere meter. Okay, so how I get this? You see that Newton comes from force, ampere comes from current, and meter comes from the length. Okay, all right. All right, so in the last slide, we derived, we see that the magnetic force is this I L B sine theta, right? So when a current carrying wire is placed in a magnetic field, okay? Now, as I is equal to delta Q over T, and if there are n particles of charge that, okay, creating this current, then I can write this NQ over T. Okay, so NQ here is basically the total charge, okay, delta Q. Okay, so if a small particle has charged this, if you multiply the total number of particles, then you get the total charge. Okay, so that's why I replace delta Q by NQ. Okay, then if you substitute this equation here, you get something like this. F equal to I is NQ over T L B sine theta. Okay, if you simplify little bit, NQ L over T B sine theta. Okay, now you know that distance over time is the speed. Okay, so here this is distance over time, so I can replace it with V. Okay, so you see that starting from the magnetic forces equation, we get this NQV B sine theta, where N is the number of particle, Q is the charge of each particle, V is the velocity of the particle, and B is the magnetic field, and sine theta is the angle between the velocity and the magnetic field. Okay, so this equation tells us that when a charged particle is moving in a in a magnetic field, there is a magnetic force. Okay, I can show you this here. Okay, so here you see this dotted point is basically the magnetic field out of page. Okay, out of the screen. Okay, now here we can change the, in the left hand panel you see that mass, velocity, charge. Okay, magnetic field strength, we can change it. So for example, if you go back, if you change it, so you see that you can make it into the screen. So you see that negative is here, negative means into the screen and positive means out of screen. Okay, and here you can change the charge. So now it is negative charge. If you bring it, it's negative, a positive charge, and so on. All right. So and then here you see the velocity and then mass. Okay, now now here you see that what happened if I shoot a, a negative charge in a magnetic field, what happened? Okay, you see that it changes its direction. Okay, so, and if I do for the positive charge, you see that it will go in the opposite direction. Okay, so one is for the negative charge, another is for the negative charge. Okay, so it tells us that when we have a charged particle in a magnetic field, it feel force. Okay, because of the force, it changes its direction. Okay, and the force is the magnitude of the force is this one. Okay, so here it is for n particle, but if you think only for one particle, it will be just qv sine theta. Okay, now the question is how we can determine the direction. Okay, so simulation tells us that when you have positive charge, it is going in one direction. If we change the particle charge, then it is going in the opposite direction. Okay, so how we know that? Okay, we can know it by using third right hand rule. Okay, so the third right hand rule is very similar to the second right hand rule. Okay, so here you see that the index finger is telling you about the v, the velocity. Other three finger is telling you about the magnetic field, and force is the thumb. Okay, now the question is, this is only valid for the positive particle, positive charge. Okay, so for negative charge, okay, uh, i mean uh, what you have to do, if we have a negative charge, first try it what will be for the positive charge, and once you know what is the direction for the positive charge, then you just switch the direction. So for example, here in this simulation, you see that for negative charge it was going in this direction, in the it goes in this direction. Okay, for the positive charge, it for the yeah, for negative charge it is going in this direction. That means for positive charge it will be going in this direction. Okay, so once you know for the positive charge, um you just switch the direction. Okay, if it is going upward for the positive charge, for negative charge it will be downward. If it is goes rightward for the positive charge, for negative charge it will be leftward, something like that. Okay, so this rule is for positive charge. Okay, so the direction of the v, the index finger is the direction of v for the positive charge. Okay, so once you know it for the positive charge, for the negative charge it's just the opposite. Okay, so here you see that in this so you can use this third right hand rule for this one. For negative charge it is just opposite. So if you determine this is for positive charge, for negative charge it will be this one, and you see that the negative charge is going downward. All right, so I'm going to stop here. In the next lecture you are going to learn a little bit more about the magnetism.